Okay, welcome back to part 3. We're going to look at section 4 and section 5. We're going to look at what happens when you change sensitivity and specificity to important parameters, and also look at the receiver operating curves, which tells you something about the test performance. So let's start with just test accuracy. It's not very difficult to see that the expression for the accuracy is given on the middle left-hand side of the page, and you get that by simply multiplying the probabilities along the horizontal line at the top and the probabilities along the horizontal line at the bottom. So if you're infected, you want to make sure that you come out positive, and if you're not infected, you want to make sure you come out negative. And so you get the expression that the accuracy is equal to the probability of infection times the sensitivity, that's in red, plus 1 minus the probability that you're infected, that's the same as the probability you're not infected, times the specificity. And if I was to plot that for a prevalence of 0.9, then you can see that the sensitivity is much more important. If you increase the sensitivity, you get a bigger effect on the increase of the accuracy than you do when you change the specificity. And that's because the sensitivity, if you look at the equation, is multiplied by pi, and pi is quite large. Now, as we reduce pi, then what happens is that the specificity becomes much more important in affecting the accuracy of the test. So there's the original diagram with the prevalence at 0.9. And as we change to 0.6, 0.4, go down to 0.1, you see now that the specificity has a much greater effect on the accuracy of the test as you increase it. Of course, to get a totally accurate test, as you can see, if the specificity was 1 and the sensitivity was 1, then the accuracy would be 1. Okay, now what I want to do is I want to go through a set of curves in which we set the sensitivity, I've highlighted that in pink, and we set the specificity in green. And in this particular case, I've set them both at 0.98. And what I want to look at is given that you test positive, the probability of a true positive, which is the probability of I conditioned on P, which is the blue line. And I want to look at the situation where you get a false negative. So you probability that given that you test negative, you come out infected. And in the middle, the line says no test. And what that really means is that if you're not doing any test, then your probability that you're infected is just equal to the prior. So if the prior probability in the population was 0.6, and you walk up to me and say, what's the chances that I'm infected? I would say it's 60%. So how do we plot these curves? I'm not going to go through the maths, but it's not difficult. I've put it on the right-hand side, so you can look at that yourself. And that's how you plot these curves as you change the probability of infection. So let's look at some performance trade-offs. So there's the figure that we've seen many times before, and we've set in yellow the sensitivity to 0.9 and in pink the specificity to 0.9. And there's the curve where we're plotting prior probability of infection along the x-axis and posterior probability of infection along the y-axis. And what you notice here is that we have quite high false negatives. If you're up above 0.6 or 0.8, you could test negative, but actually that could be a false negative, and you might actually be infected. So what we want to do is we want to reduce that, and one way to do that is to increase the sensitivity. So let's increase the sensitivity to 0.99. So that's 0.9 and 0.9, and we change the sensitivity to 0.99. Then what happens is that the orange curve hugs the x-axis more and reduces the probability of a false negative if you've tested negative. So we get a small increase as well in the probability that you're infected given that you test positive, and that's fine, and we get a large reduction in these false negatives, which is good. So now if we increased the sensitivity to 1, what would happen? Well, you can almost guess what's going to happen. This is what's going to happen. So that's the ideal case, because if the sensitivity is 1, anytime you're infected, you're never going to get an outcome which is showing that you're negative. So that's reduced the chances of these false negatives to 0. Again, a very small increase in the true positives, and the false negatives are now 0. So what I've got here is just an animation, and I took this from a blog, and I can't remember where it is, so I can't reference the guy who did it. But what we're doing here is just changing the sensitivity. And as you reduce the sensitivity, you can see the false negatives go up, as we've already discussed. So I'm changing the sensitivity between 0.9, 0.7, 0.5, 0.3, and 0.1. And I'm keeping the specificity at 0.9. Okay, so what are the requirements for a good test? Let's have a look here. So for a good test, what we want is we want the probability that you're infected, given that you tested positive, to be 1. But as it will never be 1, we want it certainly to be larger than no test. So no test is the green diagonal line. For a good test, we also want the false negatives to be much smaller than no tests. So ideally we'd like those to be 0, but that's not really possible. So we'd like it to be hugging the x-axis as much as possible. So this would be an example of a good test. So imagine the sensitivity and the specificity were 0.999. Then they really hug the outside of that rectangle, as you can see. So here's an example of a bad test. And the reason it's a bad test is because the true positives and the false negatives are all too close to the case of no test. So you're not really getting that much extra new information from either testing negative or testing positive. Okay, let's have an example here. So we're going to set the specificity and the sensitivity at 0.98, and we've got that well recognized plot now. And we're going to say, imagine that the prevalence is 0.2, and I take a test which turns out positive with approximately 92% probability I have the virus. So you get that by going to 0.2 on the x-axis and going up and reading on the y-axis, and you get 0.92. So getting a positive test means that you're probably got the virus with a 92% probability. So what happens if someone else goes along and the prior is 0.8 and they take the test and the test turns out negative? So that's good news, negative for the virus. But if you go up from 0.8 on the x-axis, on the y-axis you get roughly 0.08 on the y-axis, which means that there's a 8% probability it could be a false negative. So that's almost 1 in 10 chance that the negative test is wrong. Okay, now we're in section 5, and we're going to introduce what's called the receiver operating curve, the ROC. And if you've been working in communication networks or sensor networks, you may be familiar with this from an engineering point of view. So imagine I go back to the original example where I was looking at trying to diagnose or predict diabetes from a test by looking at the glucose level. So that was the situation that we had before. Now, how could I reduce the number of false positives? So you can think of one way of doing that is to simply change the threshold. So what I'm going to do here is I'm going to increase the test threshold to reduce the false positives. Now, it's not very difficult to see that will change all outcomes because there's 4 outcomes: true positive, false positive, true negative, and false negative. So I've increased the threshold. I'm looking for a much higher threshold of blood glucose before I will say that the person has got diabetes. So before the threshold increase, these were the total numbers of true positives, true negatives, false positives, and false negatives. And after the threshold increase, to reduce the false positives, this is what happens. And if you look, we have reduced the false positives from 10% to 0%. But it's also obvious that we will reduce the true positives as well. So in red, you can see the test results that have gone down, and in black, the test results that have gone up, because the true negatives will go up and the false negatives will go up. So it's a bit of a trade-off. So if you now test positive, at least you're 100% certain you have diabetes compared to 80% before. So with this particular threshold, you can test with complete accuracy if you actually have the virus. If you come out positive, you know for certain you have it. Now that's not the same if you test negative. If you test negative, you're only 57% certain compared to 60% before. So actually it's not too bad given this particular example. So unfortunately, as you reduce the false positives, you also reduce the true positives. Now what we'd like to do is to reduce the false positives, but not reduce the true positives. And there is a theorem, the NEYMAN-PEARSON theorem, in hypothesis testing that allows us to do this. So hypothesis testing, which I said I wasn't really going to talk much about, I'm just going to mention it in this one slide. And we have two hypotheses. We have the null hypothesis and the alternative hypothesis. So the null hypothesis would be that you don't have diabetes, and the alternative hypothesis, H1 hypothesis, would be that you do have diabetes. And so what this theorem allows us to do is it allows us to set a value for the number of false positives we're prepared to tolerate, and then we try to maximize the true positives. And when you do that, you end up getting a objective function based on a likelihood ratio. And the likelihood ratio is given in this equation, and it says decide H1, that's the alternative hypothesis, that you're saying that diabetes is present, if the function of, and I've done this in vectorial terms, the observation vector x is equal to the ratio of these two multivariate probability density functions. So the probability of x semicolon h1 means that the probability density function of the vector x, or the observations, whatever those are, and I'm not going to say what those would be in the case of diabetes. It might not map across simply. But you're looking at that probability density function of x, given that the alternative hypothesis is true, divided by the probability density function of x, given that the null hypothesis is true. And you're looking for whenever that is greater than a particular threshold. And that is where the probability of false alarm, or the probability of a false positive, is constrained to the value alpha. So that's what the NEYMAN-PEARSON theorem is. That's a bit more advanced than I've been talking about. But I just put that slide in there in case any of you were wondering about this. So let's see how the test performance changes with threshold again. To do it a bit more generally, we could look at the, well, you can call these either the histograms or the probability density function. If you know what a probability density function is, fine. If not, it's a histogram. So let's see what I'm talking about here. So I'm taking this variable y, and I'm saying when y is equal to 1, we have the red curve. This is for people who have diabetes. When y is equal to 0, we have the green curve. This is for the people who don't have diabetes. So if you look at the red curve, what's this given is, this is giving us the glucose concentration in the blood for people who have diabetes. Now, they on average have a higher concentration than people who don't. However, as you can see from that, think of it as a histogram then, you can see that some people who were y equals 1 who have diabetes, they have reasonably, not lowish, but moderate concentrations of glucose. They also have some very high concentrations. And likewise, in the green line, people who do not have diabetes, they generally have lower concentrations, but some of them have highish concentrations. So the question is, where do we put the threshold? So what you can do is you could have a guess. If those distributions were identical in shape, then intuitively the optimum position for the threshold x star would be right in the middle. And what's going to happen there is that some people in the green line who have not got diabetes, they will exceed the threshold, and so that will be a false positive decision. That is, you will diagnose some of those with diabetes even though they don't have it. Likewise, for the red line, some of those people will be below the threshold x star, and so you'll diagnose them as not having diabetes even though they do. So that would be a false negative. So we define y hat. Y hat is the estimate of the y parameter, and we'll say it's equal to 1 if the concentration is greater than x star, or 0 if the concentration is less than X star. So that area down below is the true negative rate. That's the area up until the black line under the green curve. And the false negative rate is the area that I've indicated there for the reasons I've just given. The true positive rate is the area under the red curve all the way up from the threshold X star to infinity in theory. And the false positive rate is the part that I've just indicated on the screen. So you can find those by doing integration in the normal way, because integration will give you an area. So what is the optimum threshold? I mean, the optimum threshold's in the middle if they both have the same shape, but if they don't have the same shape, how do we find out where the optimum threshold is, and what do we mean by optimum? As we start moving the threshold up and down, we will change the true positive rates, the false positive rates, the true negative rates, and the false negative rates, as we saw with the simple smiley faces and the blood glucose concentration. So let's have a look at the receiver operating curve. So what we've done here is we've plotted the distributions of those who have got diabetes and those who don't have diabetes in pink and in green. And in the bottom we've shown a threshold as being in the middle. And what we're doing in this diagram, going from the left, from the blue lines up to the pink lines, that is going to be changing the threshold. And we're going to see how the true positive rate and the false positive rate will change, because the areas will be different as you move the threshold from left to right. So when we do that, we're going to plot false positive rate on the x-axis and true positive rate on the y-axis. The true positive rate, if you think about it, is the sensitivity, and the false positive rate is 1 minus the specificity. So if we have the threshold at point A, you can see that the true positive rate and the false positive rate are both going to be 1. Why? Because if you've got the threshold as far left as you can go, then every single person will test positive. So those people who've got the virus will test positive, which gives you 1 for a true positive rate, or 100%. But those people who don't have the virus will also test positive. So you'll have a 1 for the false positive rate, which you don't really want. If you go to B and put the threshold right in the middle, then you get very close to 0 false positive rate and 1 for a true positive rate, which is what you want. And if you put a threshold right at the very end for the opposite reasons from A, then you end up with, you're at the point 0, 0. So let's look at a situation which might be near optimum in terms of the distributions for those who have diabetes and those who don't have diabetes. So here we've got two distributions which have got very, very small variance, so very, very narrow. And what that means is that as you start to move the threshold around, if you're at point A, then you have you're at the point 1, 1 for the reasons that we gave before. But it doesn't take you long, only after the second or third blue line, you've now passed that distribution completely. And so at point B, you'll have moved almost over to the top left-hand corner of the ROC curve. And so what happens is that nearly all the points as you move from the blue thresholds to the pink thresholds all pack into the top left-hand corner of the ROC curve, which keeps you as close as possible to the point 0, 1, 0 for false positive rate and 1 for true positive rate, which is what you want. So a good classifier should really, all the points should hug that top left-hand corner of the ROC curve. So what we're going to do now is we're going to take those individual threshold lines on the previous slides, and instead of having 10 or 20 or 30, we're going to make it almost continuous. So we're going to have, imagine, a million different thresholds. And as you do that, then what you'll trace out is not individual points on the false positive rate versus TPR curve. You'll actually get a continuous curve, and we call that the receiver operating curve. So you can see on the left-hand side, we have the situation y equals 1 of the distribution of blood glucose concentration for those people who have diabetes. and y equals 0 is the blood glucose concentration for those who do not have diabetes. Important thing to notice here is that the distributions are now different for those who have diabetes and those who don't have diabetes. Now, please don't email me and tell me that's not medically true. I'm just doing it for an illustration. So there's the threshold, and there's the true positive rate, and there's the false positive rate. So those are the two values that we're going to be plotting against each other, and they're equal to those respective areas. And on the right hand side, the final thing is AUC equals 0.853. That's the area under the curve. And that's a measure really of how good our test is in distinguishing between those who have diabetes and those who don't have diabetes. And the larger that is, the better. So the largest it could be would be 1, which would be 100%. In this case, it's 85.3 in the example that I'm showing you. So there's an animation of the threshold moving and tracing out the ROC curve with an area under the curve of 85.3%. So what I've done here is I've simply changed the distributions, moved them closer and further apart, and you can see how the area under the curve actually changes for obvious reasons as you do that. So when the area under the curve goes to 1, you've got the distributions well separated, and it's very easy to classify who has diabetes and who doesn't have diabetes. So here's an example of 3 binary classifiers, and clearly the one that has the largest area under the curve would be considered to be the best, and the green one, which is the smallest area under the curve, is the worst. So let's finish with one example to do with credit card fraud. So let's take a very simple case, because the bank does use systems like this, but maybe this is rather simplified. You're trying to detect whether a card transaction is fraudulent or honest. So how do you do that? I mean, you could use past history, you could use machine learning to build up a profile, but let's take the simplest possible way. One way might be to assume that if you're doing fraudulent activity, you spent more on the card than if you're doing honest activity. So here you have the two distributions for those who are fraudulent and those who are honest. Now you have to decide where to set the threshold. So let's say the threshold was £100. What you're saying is that anybody who spends more than £100, you assume that they're fraudulent and you block the card. However, some honest people might spend more than £100, so you will block them as well. Now, we assume we're trying to detect fraudulent people, so we want to increase the true positive rate, that rate of detection. So to increase the true positive rate, we want to move the threshold, the black line, way to the left. But by increasing the true positive rate, we'll also increase the false positive rate. So that means we'll detect people who are honest and we'll block their transaction as well. Now, if you don't want to do that, you move the black threshold way to the right. Now, in that case, you reduce the false positive rate and you reduce the true positive rate, which means honest transactions will all go through, but unfortunately, so will fraudulent transactions. So that's the situation that you have. And generally, they will set it pretty far to the left, because the worst outcome is that someone acts fraudulently. If a few honest customers have to make the transaction again or ring up their bank, that's considered something that's unfortunate, but it's considered something that you can live with. And I suppose it goes back to the old saying, better that the innocent suffer than one guilty person goes undetected. This is to do with, I suppose, penal reform, which says that it's better that every guilty person goes to prison, rather, and some innocent might go as well, rather than any guilty person goes free and all innocent people don't go to jail. But you can make your own mind up about that. Okay, so that's the end of part 3. We've covered sections 4 and 5. So we're going to go to the last part, which is part 4, which will have section 6, and I'll see you there.